Hello. I recently got a very basic version of the Chiplab for the 6502 chip working, so I figured I would make a quick little video. I'm going to share what I have done so far and explain what I'm planning on doing next. At this point, I have the 6502 chip able to perform a reset and begin executing code at some location that I have defined. So I'm going to show how I have the chip hooked up and how the software is interfacing with the chip. First, let's talk about the 6502 chip that I'm planning on using. I'm planning on using the dual inline package of the 6502 produced by Western Design Center. This resembles the same form factor that would have been used when the chip was first used back in 1975. I chose the DIP package because I can easily use it with a solderless breadboard, which reduces the time required to make this first prototype. All of the electronics that connect to this chip are basically dictated by whatever pins the chip exposes. So let's go ahead and take a look at a pinout which shows how the pins on the 6502 are used. In this diagram, you'll see a little notch on one side. DIP chips have a little notch so that you can figure out which side has pin 1. There are a lot of pins here, but let's start with one thing at a time. Before we do anything useful with the chip, we have to make sure it gets power. This version of the chip can run on either 1.8, 3.3, or 5 volts. The I/O pins will then interpret anything very close to whatever supply voltage we have provided as a digital 1 and anything close to ground as a 0. It's slightly more involved than this, but this is sufficient for understanding the rest of the setup. The microcontroller that I plan on using to talk to the 6502 happens to use 3.3 volts for its I/O. So in order to make everything simpler, I've decided to power the chip with 3.3 volts as well. Looking at the pinout, 2 pins in particular are necessary for power. VDD is the power supply pin, and VSS is ground. These names refer to the leads on a transistor. VDD corresponds with drain, and VSS corresponds with sink. Many chips happen to use VDD as nomenclature for supply, and VSS then for ground. So for us, we just need to make sure VDD gets 3.3 volts and VSS is connected to ground. And that's actually all that is required in order to power the chip. But we would like to confirm that the chip is running and functioning, so let's try to connect some of its interface pins. Initially, I thought I would have to build something sophisticated and very general in order to support reading writing any of the pins as required by the test program we want to run. Then I dug through my electronics drawer and found an Arduino, which will actually work perfectly. The Arduino is based around an Atmega microcontroller. It has a wealth of GPIO, or general purpose I/O pins, which can be turned into inputs or outputs via software. And this is exactly what I need to build the Chiplab. The board that I have has 13 digital pins plus 5 analog pins minus 2 used for serial, leaving 16 usable GPIO pins. This is quite a bit fewer than the total number of pins on the 6502, so I'll start by hooking up a useful minimal subset. The most important pins in order to see something functioning are the bus pins. The 6502 has 2 sets of bus pins for the address and data buses. The address bus, 16 pins, range from A0 up to A15, and the data bus pins range from D0 to D7. These pins allow the chip to communicate by setting the voltage on each pin to either high or low voltage, corresponding to a binary 1 or 0. By monitoring the address and data pins, we can get a sense of what the 6502 is doing without actually connecting it to any other hardware. The 6502 has a well-defined startup procedure. During startup or reset, it does some internal operations, then reads 2 bytes from hex FFFC and hex FFFD. These 2 bytes make up what is called the reset vector and tell the chip where to start running code. So for our Chiplab prototype, what we can do is reset the chip, set the data bus to some hard-coded value. We should see the chip read from these reset vector locations. After reading from these addresses, we should then see the chip start reading the byte specified by the reset vector value, and then continue sequentially from there. Here is a snippet of the schematic that shows how I'm hooking up the 6502. I'll talk about each of these pins next. On the upper right, we have RESB. This is the reset signal. When the chip first gets power, all of its internal state will essentially be some random value. Setting a reset forces the chip to initialize all of its internal registers. After performing a reset, the chip is in a valid configuration and can be expected to start running code as designed. Next, we have RDY. We just want to set this to a high value. A low value can be used to freeze the chip. We won't be needing this, so I'll just connect it high. Next is NMIB and IRQB. Both of these are used to control interrupts. I'm not going to be supporting interrupts in the initial setup, so setting these to high essentially tells the chip no interrupt has been triggered. The SOB pin will also be set to high. The chip has this pin which allows an external event to set the overflow bit to 1 whenever a high to low transition is seen on this pin. I don't need that, so I'll just fix it high. Next we have PHI2. Here's the first of the meaningful pins for our design. This is the main system clock. The clock is what is used to synchronize different components in the system. When the clock signal goes from low to high, the CPU does one step based on whatever it sees on the input pins. By controlling the system clock, we can control the speed of the CPU and step things forward when we want to. The RWB pin is how the chip tells us whether it is trying to read or write. A high value means it is reading, and a low value means it is writing. We won't do anything with this initially, but we will want to monitor this in order to know whether we want to provide data or read data from the chip. Finally, we have BE, which is short for bus enable. Again, we set this to high. A low value here can be used to disconnect the 6502 from a system bus. In a real hardware system, this would be used to allow the 6502 to give up control of the bus to other hardware peripherals. For the Chiplab, the 6502 is the only real thing on the bus, so we don't care about this per se. Setting it to high ensures that the output pins on the 6502 are actually enabled. Alright, that's quite a few pins. This uses up 7 of the 16 available GPIO pins. Ideally, we would be able to monitor the entire address and data bus. Given the pin limitation for now, we can start by reading only the lowest 8 bits of the address bus. In terms of successfully observing a reset, we should still see hex FC and hex FD over these 8 pins. Also, for an early prototype, I have decided to essentially hardcode the data bus. Longer term, I would like the Chiplab to be able to send data into the 6502 this way. Given the pin limitation, what I have done is wire the data pins to either ground or high voltage. This is essentially a way of hardwiring a value into the bus. Rather than setting it all to 0, what I have done is set the 2 highest bits to 1. So reads from the data bus should then look like it's reading hex C0. So with the 8 lower pins of the address bus and all 8 pins of the data bus hooked up, what remains is stepping the clock and then performing a reset. First, let's talk about stepping the clock. As I said earlier, the 6502 only changes state when the clock signal transitions from low to high. This particular chip supports a maximum clock speed in the low megahertz range, which means transitioning on the order of 1,000,000 times per second. Taking the clock speed to be 1 megahertz, this would mean the clock period would be at least 1 over 1,000,000 or 1 microsecond. Due to precision issues with the microcontroller that I'm using, I have decided to have the low time for 1 microsecond and the high time also 1 microsecond. This results in the chip running at effectively 500 kilohertz. This is plenty fast in order to perform some basic experiments. Now that we can run the chip, let's talk about the experiment that I plan to run. To make sure that everything is hooked up properly, I would like to first reset the chip. Then run the 6502 for several clock ticks. At each clock cycle, I would like to read the value off the address pins, as well as the value of the RWB pin. The Atmega or Arduino talking to the 6502 will then talk to my laptop using a serial connection and send me messages as text so that I can see on my laptop the values that were read off the address and RWB pins. I've gone ahead and written some very basic code to accomplish this, and I see what looks like the following. These A equals correspond to the value of the address bus, and this R equals corresponds to the value of the RWB pin. So prior to reset, we don't really care about what the chip is doing. But a little bit in on this transcript, we can see the address bus set to hex FC and R equals 1. This could be the read of the first byte of the reset vector. On the next cycle, we can see the address bus lower 8 bits read hex FD and R equals 1 again. These 2 sequential reads very likely correspond to the read of the reset vector that we were expecting. The next read that follows after that is with address with lower hex C0. This corresponds to the value that we had hardwired, so it does indeed seem like the chip successfully read the value that we were expecting. Following that, we can see it performing several reads sequentially starting at that address. It's hard to be certain given that we cannot see the upper byte of the address, but this strongly suggests that the chip is resetting correctly and running code at some address that we had specified. Now, the main limitations from the setup are that we did not have enough pins on the microcontroller controller to control all the pins on the 6502. And with the value of the data pins fixed, it's hard to get the chip to do much of interest. Ideally, we could expand the I/O capabilities of the Atmega so that we can interact with all the other remaining pins, including the data pins. This way, we would be able to send data into the 6502, resembling an actual program. And that's what I'll plan on covering next time. Extending the chip I/O and then adding some more surrounding software, I should be able to send real data into the chip so that the 6502 runs a real program. Hope you liked the video. If you did, please consider liking and subscribing. Even better than that is if you know someone else who you think might appreciate the video, please do go ahead and share the video with them. And that's it for now. See you in the next one.